If you saw the earlier video on function composition, you might recall that we looked at Boyles Law, which is a formula that calculates the number of chirps a cricket makes in 1 minute as a function of the temperature of its surroundings in degrees Fahrenheit. But I'm sorry, Mr. Dolbear, who needs a formula when we can just time 1 minute and count the chirps? In fact, since there is a relationship between chirps and temperature, we can actually reverse this formula and use the cricket's chirps to tell the temperature. That sounds a lot more interesting. But how would we reverse the formula? We want to take the chirps per minute as an input, where it was previously the output of Dolbear's law, and use it to find the temperature as an output, which previously was the input. This reversal of input and output of a function gives us what we call the function's inverse. Well, let's take a closer look at Dolbear's law. Here we have the formula that he came up with. On the left we have n as a function of t sub f. So n is the number of chirps per minute as an output, and t sub f is our input, the temperature in degrees Fahrenheit. In order to convert temperature into chirps per minute, we apply the function rule, which says subtract 40 from the temperature and multiply the result by 4, and that'll give us the number of chirps per minute. So this says that the temperature is the input to this function, the chirps per minute is the output of the function, and the function rule is basically the chirps per minute formula. Now, if we want to turn this around, we want to find the temperature as an output by knowing the chirps per minute as the input. And so this reversal of input and output is what we call function inverse, and this is now going to give us a temperature formula instead of a chirps per minute formula. Do this graphically. I'm going to go ahead and plot the points from the table on the previous slide, and I'm going to do that in purple and connect those points together with the function curve. So what you see in purple is basically Dolbear's law that uses the temperature in degrees Fahrenheit along the horizontal axis as an input and gives us an output in chirps per minute along the vertical axis. So we're going to take one point at a time here and find its inverse. And so I'm going to start with this first point where we see we have an input of 60 degrees Fahrenheit and an output of 80 chirps per minute. In order to find its inverse, I want to use 80 chirps per minute as the input along the horizontal axis and 60 degrees Fahrenheit as the output along the vertical axis. So that looks like this. I'm going to plot a point in green at that intersection, and our green function that we're going to be building here now is really the inverse of Dolbear's law, which is what we were looking for. We want to be able to input chirps per minute and output degrees Fahrenheit. Notice though that the labels on the scale right now are degrees Fahrenheit along the horizontal axis and chirps per minute along the vertical axis. We want to reverse that for our green scale. And so in order to do that, I'm just going to go ahead and mark them up here in green. And so in addition to changing our inputs and our outputs on the coordinate points, we need to make sure that we do that on our scale along the graph axes. Okay, so now if you notice we've got that point graphed in green. I'm going to go ahead and bring over the table for the inverse function so that we can keep track of that. So now on the right, surrounded by green, you see the table that has the input of chirps per minute on the left column and our output in degrees Fahrenheit. Okay, next point that we have is 70 degrees Fahrenheit as an input, 120 chirps per minute as an output. We're going to go ahead and reverse that. And so I'm going to have 120 chirps per minute as an input, 70 degrees Fahrenheit as an output, and I'm going to mark that point. We'll do the same for the third point. Third point has an input of 80 degrees Fahrenheit, output of 160 chirps per minute. We'll reverse that, where we have 160 chirps per minute as an input, 80 degrees as an output, and finally our last point, 90 degrees, 200 chirps per minute. Reverse that, 200 chirps per minute as an input, 90 degrees as an output. We go ahead and draw the line, the graph through those points. And so now we've got the inverse function plotted. So the inverse function, again, takes chirps per minute as an input and gives us the temperature as an output. Now, when we mapped the original purple points onto their new inverted green points, you notice what happened is that we reflected those points across the diagonal line y equals x. And the process of reflecting that really is the way that we draw inverses of graphs graphically is we simply switch the input and output values of each point's coordinates. So we've got those points for our inputs and outputs of the original Dolbears, and if we just reverse the x and y and replot those points, we end up with the other points that you see there. So doing inverses with tables and with graphs is actually pretty easy. With tables, we just switch the columns from input to output. And with graphs, we reflect all of the points in the curve over the diagonal line y equals x. How do we do this algebraically? How do we take a formula like Boyles Law and create the formula that we're looking for as its inverse? And it's actually pretty easy. In fact, it really is based on switching the inputs and the outputs. We're basically just going to solve for the input variable. So now the input variable becomes our output, and the output variable gets buried somewhere into the expression as an input variable. So let's look at an example here. We're going to take Boyles Law, and I'm going to simplify the left side just a little bit and call it just n. So our output right now is n, the number of chirps per minute. On the right, we have 4 times the temperature minus 40. I'm going to go ahead and divide both sides by 4, and then I'm going to add 40 to both sides, and now that's isolated our input variable, which is the temperature, and now is giving that to us as an output. And so we can really rewrite this thing as the temperature function T sub f of n, where n is our input, and that formula is going to be to take n, divide it by 4, and add 40 to it. So if we go back to the beginning of the video, we were looking for exactly this function. What is T sub f of n? And by solving our original function for the input variable, we've actually been able to find that expression. All right, so let's go ahead and see if we can outline a procedure to find f inverse when we know the original function f. So we're going to use an example here. F of x equals square root of the quantity x minus 4. So the first thing we're going to do is just replace f of x with y just to simplify things. So we're just going to rewrite this as y equals square root of quantity x minus 4. Now we're going to switch x and y. So even doing this algebraically, we're still following this concept of changing the inputs and the outputs. And so we're just going to rewrite this with x in place of y and y in place of x. So x equals the square root of the quantity y minus 4. Now we're just going to solve for y. So I start with x equals square root of y minus 4. I square both sides to eliminate the square root. And then I'll add 4 to both sides so that I can solve for y. And the last thing I'm going to do is replace y with the notation f inverse of x. And so my final answer is that f inverse of x is x squared plus 4. If we go ahead and take a look at a graph of this, we can see that the diagonal line y equals x forms a reflection from the original function in purple, square root of x minus 4, to its inverse, f inverse, which is x squared plus 4. Now notice that x squared plus 4 is only half a parabola. What happened to the other half? This has to do with what we call one-to-one functions, and that will be addressed in the next video.